Great. I'm thrilled to be here to welcome old friends and new friends in this technical session of the Wallenberg Prize 2022. It is a great honor to welcome you all. Yesterday we had a wonderful banquet. Today we have a second banquet, a banquet of ideas. And I think really we have an amazing lineup of speakers. We're going to have two parts. In the first part, a technical session related more to the technical developments. And in the second part, we're going to tackle other aspects related to wearing wood. That's the subject of today's session. Just to let you know that there are online participants. There are a little bit more than 100 delegates attending online, so the session will be recorded. I also ask you to turn off your cell phones and be open-minded. I think this will be an amazing session. At the end, we're going to have 30 minutes of questions and answers. Without further ado, I would like to welcome Mr. Marcus Wallenberg, Chair of the Wallenberg Foundations, to do the opening.
Thank you. Thank you, Orlando. Good morning. Can you hear me? Yeah, that's perfect. Good morning, ladies and gentlemen. Great to see you here this morning. This prize, as we discussed yesterday, is really all about trying to further the interest around forests and forest production and forest industry and the possibilities about the future. I think that is one of the key messages that we have over time been able to deliver, and I think it's only a start of what the possibilities are for the future. Johanna Buchert and the whole team in the selection committee, I think, has been putting together what I think can be a very interesting and fruitful program for today, wearing wood and the world of wood-based textiles. I think that this will address both big and small companies, and academia and industry has an incredibly important role to work together to find new ways to use this recyclable and really sustainable material that we can do things with for the future. And I really hope that we will be able to continue to develop technically and industrially what we are all working with on a continuous basis. We have a very tricky situation in my mind. We have a political force driving the question around forests in one direction. And I think it goes a little bit to the contrary, and this is a worrying fact. There are two sides to this coin, as we know. On one side, the whole sustainability part. On the other side, the potential of using the wood fiber as a potential material to solve a lot of the sustainable questions for the future. And these two forces have to meet at some point. And I think this is something for us working with this on a daily basis. We have to keep an eye on this and make our voices heard in this debate, because otherwise it might fall in a different direction that we are really wanting to see. As part of the mission for the prize, we have set out the wish to have young researchers joining this. And when I look at other businesses that we are involved with, it's obvious that many of those businesses, different industries, are benefiting from the involvement of researchers, young researchers, who bring in new ideas and bring in the entrepreneurial aspect of what those industries and how those industries can develop. It seems to me that in the world of textiles, that could be, as just one example, but I think in many other aspects, the possibility to see young researchers turning into their ideas into entrepreneurial efforts in one way or another will also for this industry, or the forest industry, be a very, very important part. So I really want to welcome all of you to be here. At last, I really want to thank the selection committee for bringing such a wonderful group of good speakers together, really interesting, and thank you for traveling from very far apart to join us here today. And thereby, I'd like to turn over the word to Orlando again, and thank you very much for being here.
Thank you very much, Marcus. It was a wonderful opening, a lot of wisdom. And now I have the distinctive pleasure to introduce one of the laureates, Professor Herbert Sixta. We're going to call him Herbert during the sessions. We're going to use the first names to make this a more familiar exchange. And you already know about Herbert. He is Professor Emeritus in Aalto University, and he will be talking for 30 minutes about the favorite subject of his. So please, Herbert.
Yeah, thank you so much, dear Orlando, for this kind introduction. Ladies and gentlemen, I'm overwhelmed to be here. Thank you for this enormous and nice event, especially grateful to Marcus Wallenberg, of course. Yes, ladies and gentlemen, it's my real pleasure to introduce ion cell and its possible place in the textile industry given the particular challenges of climate change. As an introduction, I would like to start with a short historical overview on textile fibers and spinning technologies. As you certainly know, in the early history of mankind, textile fibers were exclusively made of natural fibers. That's quite obvious, but it was evidenced by a 30,000-year-old flax fiber found in the Republic of Georgia. That's the first experimental evidence of textile fibers. And it's also well known that the Sumerians were able to spin and weave flax fibers many years back. And since the Neolithicum, natural fibers as we still use them today, like cotton, silk, and wool, have been used as textile material. However, the development of the industrial production of textiles is a relatively new invention, and it was fueled by a strong population growth in the early 19th century. All began actually at the 1889 Paris World Exhibition, where Count Hilaire de Chardonnay, for the first time, presented a cloth entirely made of synthetic fibers. It was cellulose nitrate, and he called it artificial silk. However, due to high flammability and also high costs, it was soon replaced by viscose fibers. And viscose technology has been developed by three gentlemen, Cross, Bevan and Beadle in UK. And you are aware that this technology is still the most dominant technology for the production of man-made cellulose fibers. The development of synthetic fibers goes back to the 1930s, where the very famous chemist Wallace Carothers invented nylon 6,6, and 10 years later, John Rex Winfield invented polyester. So that was the start of a really, let's say, growing industry. Although the first direct cellulose solvent, N-methylmorpholine N-oxide, has already been patented in 1939 by Charles Grenacher, it took another 30 years until this idea was took up by Kodak, and they used this invention to develop a lyocell process. But another 23 years later, the first commercial lyocell plant came on stream in Mobile, Alabama, in US by Courtauld first, and soon later by Lenzing in Heiligenkreuz, Austria. And it's still the most, let's say, awarding technique for the production of man-made cellulose fibers. 3 different spinning technologies produced by regenerated cellulose fibers. Dry spinning, as you see here, there a low boiling solvent evaporates in a spinning chamber by the introduction of hot air in a countercurrent flow, thereby gradually solidifying the filament. This technique was used for the production of cellulose nitrate and is still used for the spinning of cellulose diacetate. Of course, the most dominant spinning technique is the wet spinning technique, and it is in commercial use for the cuprammonium process and the viscose process, but also for new developments, for example, cellulose carbamate, and a variety of different spinning technologies using diluted sodium hydroxide as a cellulose solvent, like tree-to-textile, biocellsol, but also Spinovo, they use a pulp suspension for wet spinning. And last but not least, dry jet wet spinning. It was adopted by the lyocell process, and the lyocell process is connected to the use of a so-called direct cellulose solvent. And there, the spinning dope passes the air gap, you see that here, and thereby a strong stretching is possible, which leads to a high orientation of the cellulose molecules parallel to their molecular axis, which is a prerequisite for strong and powerful fibers. Now I would like to give you a short overview about the global fiber market, and it's amazing to look back to the last 120 years of fiber development. Until the 1990s, the per capita fiber consumption was clearly dominated by natural fibers, and only then the synthetic fibers basically started to be the dominant fiber species. Today we have almost a share of 70% on the global fiber consumption. Man-made cellulose fibers, in particular viscose fibers, they peaked around 1970s and dropped to a minimum in the year around 2000 due to many closures of plants, especially in Central Europe, Russia, Americas. And during the time, some of the companies also made their homework and cleaned up the sites, which was a prerequisite for the steep upswing, what you see here after 2000, where a lot of new installations were built, especially in Asia and China. The biggest growth by 2030 is predicted for cellulosics. Why? The first reason is cotton fiber stagnates in the growing and in the consumption. And on the other side, the demand of cellulosics further increases. So that's a good opportunity also to develop new man-made cellulose fiber processes. When evaluating a new fiber or even fiber category, then it's very important to assess its quality in reference to the main reference fibers. Sometimes that is forgotten, so we just develop new fibers and we don't care what are the reference fibers, how they look like. So that's very important to have an overall look at that. For the sake of simplicity, I selected the strength properties as the major criterion for the fiber properties. And here you see the dry and wet tensile strength of the natural fibers. Hemp and flax show very strong tenacities, particularly under wet conditions. even higher than under dry conditions, while the major synthetic fibers also show excellent strength properties, and especially high toughness values due to high extensibility of the fibers, which is very unique for synthetic fibers and is very tough to achieve with cellulosic fibers. While at the same time, regular man-made cellulose fibers show quite low properties, mechanical properties, and especially under wet conditions, with two exceptions. The first one is what I mentioned already, the lyocell fibers. And due to their high orientation, they have a nice and high wet tenacity. And a specialty viscose fiber, we call it the Supercore 3. It's used for the reinforcement of tire cords. So these two are exceptional with regard to the properties. Yeah, now what is the fate of the textiles at the end of their service life? That's the $1,000 question. And currently, the textile industry predominantly follows a so-called linear business model. What does it mean? A linear business model means that the textiles basically immediately end up in landfill and incineration after only an average wearing cycle of 20 washes. That's an average, of course. And currently, the amount of textiles which are given a second life is very low. It's about 3.5%, and most of it is concerned the resale or the rental. You see that the linear business model is getting an outdated model, and we need to look for alternatives. Why? Because first of all, we have a loss of value due to this short life cycle, and the second is, of course, an enormous pollution. So therefore, we have to work for alternative concepts. So more in detail, where do the fibers finally end up after use? Of the 84% of the fibers are either incinerated or they are landfilled, of which 1/3 consists of natural polymers, cellulose or protein fibers, and 2/3 of synthetic fibers. And the problem associated with synthetic fibers is not that they are not recyclable. That's relatively clear, and it's possible, and even easily possible. But the problem is the almost non-existing biodegradability. And that concerns many of the synthetic polymers. And here you see the most important representative of synthetic fibers, polyester. So basically, with the standard tests, no biodegradability. And that is about to be confirmed in long-term investigations currently done by the Scripps Institute close to San Diego. There are deep-sea investigations of different material swatches, and you see here just the comparison between polyester and lyocell. But even that is not the only problem, but it is clearly associated with the most important problem associated with synthetic fibers, namely the release of microplastic fiber. Yesterday, I had the privilege to sit next to the Queen, and she told me that her 10-year-old granddaughter refuses to eat fish because she said fish contains plastic. Yeah, so that is really an issue, and we have to work on this also from the fundamental point of view to avoid the release of microplastic fibers upon laundry. Now I would like to briefly introduce the ion cell fiber process and show step by step what role this process could eventually play in the transition to a sustainable textile industry. The most important feature, or one of the most important features, is the use of a powerful solvent, direct solvent for cellulose. And we selected a so-called protic ionic liquid, with high thermal stability, with a high dissolution power, and with an environmental footprint very comparable to N-methylmorpholine N oxide. Currently, we are working with 3 of these protic ionic liquids, and both so-called amidinium and guanidinium-based cations. And the development of these solvents is fully credited to my colleague, Professor Ilkka Kilpeläinen, and his team. Another aspect of the lyocell technology compared to the wet spinning processes is the fewer unit operations. So it's a much simpler process, and it's a closed system with only one chemical input. That's the solvent, and that we have to keep in the cycle. And this is also a difference to the current NMMO-based lyocell, because they have to add stabilizers and also other chemicals for the regeneration of ion exchange resins, for example. So we think that the concept here is quite future-oriented. The decisive unit operations of the ion cell process comprise both, first, the production of a homogeneous cellulose solution to ensure stable spinning, and of course the air gap spinning concept. The manufacture of these highly viscous spinning dope requires high shear forces, really high shear forces, and that is achieved in a kneader or in an extruder, for example. These are 2 examples, it's not complete. And under the microscope you see a very fast and complete dissolution. Here you see pulp fibers which basically disappear upon time, and when it's black, it's fully dissolved. So what are actually the key innovations of ion cell? The first one is what I mentioned already, the selection of the most appropriate direct cellulose solvent. I talked about that already. And the second one is the adjustment of the flow behavior of a viscoelastic fluid, that's the spinning dope, inside the capillaries of the spinneret and also in the air gap. So what kind of flow behavior do we have? In the capillaries, we have a dominant shear flow, and that means that the viscosity decreases upon the deformation rate. Why? Because of the gradual disentanglement of the polymer chains and of course also their pre-orientation. And that depends on the geometry of the spinneret and of course also the conditions during the extrusion. While in the air gap, we have a dominant extensional or elongational flow with the unique observation that this extensional flow increases upon the increase of deformation rate. Why? Because of the parallel orientation of the molecular chains. So these 2 different flow patterns we have to tackle, and that's the innovation of this process. And here you see 2 examples of a stable spinning in the air gap. I hope you see it. And what you should observe is that the filaments exiting from the spinnerets align in parallel as soon as you apply a stretch. And here you see the goddets where the stretch is applied. And the stretch ratio is much higher than in all the other spinning technologies, which ensures a high molecular orientation, a prerequisite for high strength properties. Besides the high tenacity, ion cell fibers have this natural luster, which not always is a desired property, but in most of the times. Now, what is the sustainability? We claim sustainability. What is the sustainability of the ion cell process? The sustainability is ensured by a complete closure of the solvent and the water cycles. Here you see a scheme. I promised it's the only one. It's a closed cycle of the solvent. And in numerous trials, my dear students and colleagues have tested the recyclability of the solvent. Using here, for example, this thin film evaporator. And at the moment, we state that the recovery rate of the ionic liquid is around 99% or above. This is, of course, with the restriction that this is a batch mode, where we simulate a continuous flow, in this case, for 20 cycles. Now I come to the next topic, which concerns the raw materials. This is very important, and we will hear a talk from Frank Meister after my talk, how important the properties of the raw materials, for example, wood pulp, is on the processability and on the final products. I was so lucky in Aalto University that I had a team. Even though we had a small device for spinning, we could produce, look at that, a numerous amount of nice dresses. And that was only possible by the help of my students, my researchers, and also by the help of the researchers from our School of Arts, the Department of Textile Design, who took care of our yarns, what we produced, and then manufactured fabrics through weaving, through knitting, then finishing, dyeing, everything, designing, and even the fashion show. They covered everything. So from wood to fashion show, that's the credo. Of course, we need to look ahead, and the future is a good balance between the use of sustainable wood pulp from sustainable forests and recycled textile wastes. And so I show you a selection of different cellulosic wastes we were able to upcycle. The first example concerns cardboard waste. That was in the very beginning when we started, and you see it was possible that we could convert the cardboard waste to staple fibers, to yarns, to fabrics, and they look a little bit different, so they have different color. The reason for that is the different lignin content, which also shows that our process can also take in other biopolymers like lignin, hemicellulose, chitin, chitosan, and so forth. And the difference in the colors, our designers liked it because they could play with the colors, the different yellowish, brownish colors, and that was because of the different lignin content. Another important example is the recycling of more or less uniform textile wastes. In this particular case, it was the old jean. And in this case, we not only recycled the cellulose, but also the wet dye. And we could basically preserve the color, and you see this nice baby shirt, and that is from the old jean. Another example, or two other examples of post-consumer cotton waste. In the upper one, a more difficult task, which was solved by Simone, my PhD student at that time, and her task was to concomitantly recycle the reactive dyes. And reactive dyes is a different issue because they are covalently bonded to the cellulose, so it was not so easy. But still you see that it was possible, and we had a small fading of the color. What you also see on the right side, you see, I don't want to give you the details here, but there is a yellowish area and a greenish area. The yellowish area symbols the strength properties of the virgin fibers on the market, and the yellowish, the strength properties of the upcycled cycle. And you see, okay, without seeing the numbers, it's up and to the right. So it's better than the virgin colors, virgin fibers. And the same applies to the wasted cotton roll towels. Also there, we had very successful recycling results. The same also with hemp waste, we played this through. A very important invention was also the selective separation of cotton polyester. Why is that so important? Because these are the most abundant blends on the market, so we need to look for solutions to recycle both parts of this blend, both in this case polyester and cellulose. And through our process, a selective dissolution of the cellulose is possible, which directly leads to the spinning of ion cell. And the residue is pure enough to be also further utilized either by chain extension or repolymerization. This is a very unique example. And the Bank of Finland and the European Central Bank contacted us and said, okay, every year 6,000 tons and more of old banknotes are incinerated. This is high value cellulose. Come on, what to do with that? So we can't always incinerate them. And so they supported us and our student here, and indeed it was possible to recycle the banknotes and produce yarns and fabrics. And the last example I show you is also quite nice, because this is what I didn't know. The production of luxury textiles, they use a lot of cashmere wool or silk. And by producing the products, there is a lot of loss of these valuable fabrics. So they can't use them, maybe in insulation or something like that. So it's a waste of material and cost. So we decided to use this in a blend with the cellulose and produce the nice hybrid cellulose protein fibers. And to our surprise, we found that by blending the proteins with the cellulose, the surface hydrophilicity was completely changed. And also what is an issue in lyocell, I don't know if you know that, namely the tendency of fibrillation, and that was massively reduced. So that was a great achievement. We never thought about that. Now I come to my end. Which role, I come back to my first question, can ion cell play in the business model predicted for 2030 and beyond? And of course that must be a circular business model, and according to a recent Ellen MacArthur study, it's predicted that 23% of the global value of the textiles will basically given a second life, which does not look very much, and mostly achieved through resale and rental, not due to recycling in that sense. But still, even this share of 23% represents a value of $700 billion US, and what is even more important, a decrease in greenhouse gas emissions of 340 million tons. Now, before I would like to come to the final end and make my final assessment about ion cell, I want to pick up this idea from Ellen MacArthur. They pinpointed down to 3 ambitions. Ambition 1 is to ensure biodegradability through renewable resources. I think that is fulfilled. Do you agree? Okay, we can say yes. So there are 2 more ambitions, and they are governing the longevity of the textiles. And the first criterion is the mechanical strength. So our hypothesis is with increasing mechanical strength, the longevity of the textiles is also positively influenced. And the second is, of course, also to increase the utilization rate by chemical recyclability. And we will then step by step address these questions. First, the higher longevity through higher mechanical strength properties. To this end, we need to return to our graph showing the list of representative fibers on the market related to their strength properties. So you remember this graph? And in our development, the ion cell fibers, we centered in the development of a so-called regular fiber, which is a low-cost fiber, so with wood pulp of relatively low purity, and that is our standard grade. And then, of course, also we started to investigate the so-called high tenacity grade, especially high tenacity in the sense of high toughness. That's important for textiles. And these 2 grades, you see, fit quite well into the upper range of this mechanical properties of these fibers. So I would say, and together with the more detailed showing, the stress-strain behavior of ion cell clearly exceeds the stress-strain behavior of commercial cellulosic fibers on the market. So we could conclude, in short, yes, ambition 2 more or less fulfilled. And then the third ambition, we have to look if the chemical recyclability is also ensured. And we took that very seriously, and we started 2 years ago with a big program with 2 students from different fields to test the recyclability of our own fiber following this clear scheme from pulp, ion cell, staple fibers, yarns, fabrics, and 50 washi. Can you imagine how much work that is in the laboratory? Unbelievable. So we had to really produce a lot of fibers and produce fabrics, 50 washes and so forth. And we managed to achieve 2 complete cycle steps. That's enormous. And of course, as expected, the so-called degree of polymerization is affected over the stages. But, and that is where I have to use my pointer, very amazing. You see here during the washing, 50 washes, basically no change in the degree of polymerization occurred, which is a clear indication that these fibers have a high durability. So that was amazing. We did not expect that. Together with more detailed GBC measurements, and you see also here that the tenacity was still on a good level, even though we used the degraded cellulose as an input for the production of ion cell fibers. But together with additional measurements, we calculated the so-called chain scission. When you have one molecule, then you can easily calculate how many scissions you have per molecule. And with this information, you can calculate the number of chemical cycles with different assumptions. The first assumption was an initial viscosity of 600, then we end up in 2 full chemical cycles. When we increase it a little bit, then we have 4 cycles. Of course, this is a theoretical consideration. In practice, we would run the ion cell process at constant dP. That means that we have to compensate for the decrease in degree of polymerization by the blending with other substrates. But this is what we found out and experimentally verified 2 chemical cycles. So that means that we can make our final conclusion. Yes, ambition 2, longevity through highest tensile strength, yes, we can say that has been achieved. And of course, we have to further improve that. And also the chemical recyclability, the first indication is, yes, it was approved, and we can say it is really achieved. So we can say that ion cell has the potential, at least, to allow a real prolongation of the life cycle of the textile fibers. Now, what is the future of ion cell? A short outlook on that. And we were quite busy, thanks to our generous support from Aalto University, to basically build up a pilot plant during the pandemic. So our engineers, our students utilized the time and built up a nice pilot plant. And a few months ago, we founded a startup company named Ion Cell OE. Yeah, quite logical name. And now the real reality starts, because from beginning of next year until end of 2024, we have to show that this process is capable of running in a continuous mode, that the recyclability of the solvent is as we have predicted in the batch mode. That is, of course, clear. And if everything goes out as we think and hope, then in 2025, we will start with the next steps. So, ladies and gentlemen, thank you so much for your patience. Thank you for basically attending this nice conference. But my special thanks go to the Marcus Wallenberg Committee for awarding this prize. Of course, to Aalto University and the Finnish government for their great financial support, for the ERCO Foundation, which enabled the building and financing of the pilot plant. Very happy about that. And of course, to my colleague Ilkka Kilpeläinen and his team for the successful and excellent collaboration. And this is the most important treasure you have at the university, good students, and we had a lot of them, and researchers and colleagues who contributed to this work. And last but not least, I have to say, Lenzing AG, without having worked there for 25 years, plus 5 years, 30 years, it would not have been possible to enter into this project. So I'm very, very happy about that. And Lenzing AG also publishes a scientific journal, Lenzinger Berichte. And to my mind, it's the highest level publication on these issues. And please have a look. It's online. You can access it. And the latest edition also gives you some insight about my life at Lenzing and, of course, also later. And finally, also thanks a lot to my family who endured my Finnish diaspora for 15 years. Thanks a lot.
Thank you, Herbert. What a great summary. We really enjoy it. Wonderful prospects. I think a lot of things for us to think about and the future developments that we could expect from this development, the ion cell development. I was thinking that it is funny that in the 1800s, paper was made from old rags and discarded clothing. Right? Now we're reverting this. Now we use discarded paper to make textiles. So it's a little bit paradoxical. Very, very, very interesting. Now I'm very pleased to introduce the next speaker, continuing with the technical aspects of today's event. I'm very pleased to introduce Dr. Frank Meister. Frank is the head of chemical research department at the Thuringian Institute of Textiles and Plastics. This is a private research organization. This is very important to highlight. This collaboration between industry, universities, and research institutes like TITK. So welcome, Frank.
Good morning, ladies and gentlemen. After this firework of new ideas and inspiration, it's not so easy for me to show some technical aspects inside this direct dissolution process. Nevertheless, I will try to give more insights in the raw materials and the impacts on dissolution for cellulose man-made fiber spinning. First of all, congratulate again the Professor Herbert Sixta and Professor Ilkka Kilpeläinen on behalf of the whole TITK team for this awarding a Marcus Wallenberg Prize. It is a real good decision of this committee for this year. Let's begin again with this outstanding merits of the ion cell technology. You see again, I have taken another presentation of this process to have these cycle idea inside. And inside this cycle, I will speak more about this interaction between pulp production and fiber spinning. Nevertheless, ion fibers are belonging to wood fibers, and the most important thing, not only is this very prosperous perspective, also this kind of wood fibers keeps the CO2 in the loop. That's very important for today. Suitable pulps, we have heard it, are mostly made of wood, and all kind of modern wood pulping, a sulfide process and pre-hydrolysis craft process could be applied. We have also seen that other kind of material could be used, especially recycled cellulose materials coming from cotton or cellulose man-made fibers, and that's a very huge advantage of this kind of direct dissolution spinning. Let's start with characterization of these pulps in more detail. From lignocellulose and also from textile waste, these materials have to separate from side components and impurities before it could be used as a pulp. You see it here in these picture that at the beginning, coming from wood, there's a mixture of different components, mostly lignin, cellulose, and hemicellulose, and you will end up in the pulping process with the cellulose, which is consisting of macromolecules. Cellulose itself, it's a semi-crystalline polymer, and it's consisting of chains of different chain lengths. And for an optimal dissolution, physiochemical and structural properties have to be adjusted to comparable values. What are these comparable values? Or even what are the pulp properties affecting the dissolution? On the one hand side, these are molecular properties like degree of polymerization, molecular weight distribution, or even the properties of the dopes made of this pulp. This affected more or less the dope quality, viscoelastic flow, chain, detangle speed, deformation, relaxation rates. We have already heard that these are very important values, especially also for spinning in the air gap. But also the chemical composition and the purity could affect these dissolution behavior, especially if you think to a more technical process. That means to repeat the dissolution and the spinning properties. And of course, we have heard there's a danger for solvent decomposition, and that is mostly caused by the purity of the pulp. But also economical values like recovery rate and these very high economic efficiency of this kind of processes. Crystallinity or crystalline structure and fiber homology are most important, especially for solvent migration rate and a perfect dissolution state. Having this in mind, we investigate the dissolution of pulp in this direct dissolution process. I have to stem at this side. We do it not in the same manner as Herbert has shown. That means to use ionic liquid for the dissolution. We use the common solvent, NMMO, and at any time we have calculated these parameters on the basis of a dope with about 12% of cellulose inside. But we have also focused on different kind of raw material, especially these agricultural residues, straws from hemp and also from linseed flax. The most important area of so-called soft or hardwoods or even paper pulp, and of course also recycled cotton were in our focus when we investigate these processes. That means we also focused on typical kind of commercial available pulps for our selection. And I will not go too much into these details, but I will give some more parameters which are most important for that. We have focused on a degree of polymerization in this range, also Herbert has mentioned. And we also have this polydispersity, which is a very important property of pulp, especially if you have these for direct dissolution. You see, we have selected polydispersities in the range of 3 to 6, and the polydispersity is a quotient of molecular weight, the weight average and the number average of the molecular weight. It is also our aim to have a high cellulose content, higher than 90%. You see, we have not in all cases, and I will show that there are also some opportunities if you not have such high purity of the pulp. We have low Hemi content in the range of 4 to 10%. That is more important from the technical point of view, because if you have very high hemicellulose content, there's a danger that they are not precipitated again after a cycle, and so in technical processes you will increase this concentration over a number of different dissolution and spinning cycles. And of course, low metal salt contents are required. That means especially heavy metal have this property that they can decompose the solvent. That's why they should limit it below 10 ppm. And the same is valid for alkali and earth alkali metal concentration. But here it is more a focus of the more easy solvent recovery. What are the good opportunity to compare pulp dissolution behavior by its molecular properties? And you're well familiar with this. Cellulose as a native polymer is characterized by different degree of polymerization. That means different kind of cellulose or even of pulp are different in their individual mass. And that is very different from the low molecular substances. That's why the most important parameter after degree of polymerization is molecular weight distribution. You see in the picture two different kind of molecular weight distribution of two different substrates of cellulose. And the molecular weight distribution describes this frequency of all polymer chains representing a specialist chain length or even molar mass. Number average molecular weight or even viscose average molecular weight, and these weight average weight, and finally so-called centrifuge average of the molecular weight could be measured by the same statistic, and that's why these values are comparable, and you conclude from the numbers of these averages special effect of different kind of pulps inside the dissolution. In this curve, we have on the left-hand side low polymer or short polymer chains, and on the right-hand side, the long polymer chains. And you will see, especially if we change to the dissolution, these values are very important. From these molecular weights, you can conclude we have here also used these paper pulps, and it is not surprisingly, but untreated paper pulps present the broadest molecular weight distribution. You see it in the blue curve, and we found a way to degrade these paper pulps by an enzyme pretreatment to coming nearer to the requirements I have mentioned before. For this wood pulp, you see a moderate or an optimal molecular properties, and that is valid also for the hemp chive pulps we investigated. The differences between these two pulps could be detected on the low end, of course, also on the high molecular slope. Finally, recycling cotton and linseed, this, another group of this pulp we investigated, show the narrowest distributed cellulose, and again I will show what it means for the dissolution behavior. That brings me to a somewhat difficult issue inside the characterization of the impacts of pulp on dissolution, and that is this question of deformation or relaxation behavior of cellulose dopes. For spinning solution as well as for ion cell dopes, it is most important that they have a viscoelastic flow. That means this is mandatory for a process which is called dry jet wet spinning or air gap spinning. The viscoelastic flow of dope presents these characteristics of the pulps, that they present different degrees of movement of the polymer chains when applied strain. And you see the experiment which is behind that you have to set a deformation step, and you look how reacts this dope in this relaxation behavior. That means in deformation the dope applied strain, and in relaxation it the induced stress could be detected. Relaxation means it describes the recovery of the polymer melts or solution when deformation kept constant. And you see from the picture that there is in a polymer not only one relaxation behavior, because we have different lengths of these molecules, we have also different relaxation behavior. And that brings us to a very interesting opportunity to characterize these behavior or these impacts of pulps in dissolution. That is the so-called relaxation time spectra. We measured that very easily, and we could characterize 3 different groups of pulps. The first one, it was the paper pulp, which presents the broadest molecular weight distribution and the highest viscoelasticity. You can see, even if we have this enzymatic treatment, we have a very low deformation rate and an open relaxation time spectra. That means that especially the highest or the longest polymer chains do not give any contribution to the viscoelastic flow in this area we have investigated. For these wood and hemp dissolving pulps, we could indicate an optimal viscoelastic flow. That means a well-balanced deformation rate too. And finally, the third group where we have the dissolving pulps originate from recycled cotton and oilseed flax, which present highest quota of viscose flow. That means a high deformation and a fast relaxation. That is very important to take in our mind if we change to the effect of deformation rate at the fiber spinning process. You see on the, left-hand side a scheme of this air gap spinning, a little bit other than Herbert has given. Nevertheless, we have at the upper part the spinneret, where the shearing stress dominates. We heard it also from the lecture of Herbert. And afterwards, we have this air gap. And in this air gap, deformation is more relevant. It becomes constant at the end of this drawing process, and the relaxation of the polymer dope set in. Low relaxation is typical for broad distributed pulps, allowing a spinning at a long air gap length. And if you change to typical narrow distributed pulps, it leads to limitation of the length of this spinning of this air gap, and so you have also the opportunity to change it, or you have to change in order to be able to spin such materials, such pulps as coming from textile waste. Nevertheless, besides the effect on the deformation and relaxation, you have also some other parameter which can affect this deformation process inside the air gap. And these are typically temperature, of course, and humidity, or the conditioning inside the air gap, but also the dope concentration could affect these properties in the air gap. That brings me to the end of my presentation. I acknowledge my team, especially Mrs. Dr. Kosan, which she has investigated all this pulp and dope characterization. Frank Günther Niems, he is our head in process technology, and all the other guys for continuous spinning trials or process engineering. Michael Sturm, that is our PhD at the group of Ilkka Kilpeläinen, and he is very responsible for these new solvents are used in ion cell. And last but not least, all my former colleagues, those have developed this basic process are acknowledged at this time. Thank you very much for your attention.
Thank you very much, Frank. It's very interesting to learn the complexities of molecular weight effects and also the incorporations of other types of fibers beyond wood-based fibers, right? Non-wood fibers, for example. So thank you for your insights. So the next part before going to the break is to acknowledge a great session that we had yesterday with the young researchers. We had about 30 presenters coming from many different areas in the world, and I think it was very exciting to see the innovation and the excitement that the science brings all us together, and you see a little bit of that in the posters that are outside. And what we're going to do next is to award the best presentation, 3-minute presentations. Giving talks for 3 minutes is very challenging, and I think we are going to see the best poster. We're going to watch the video, and for that, my colleague from the selection committee, Joris, will take then charge and do the announcement. Thank you, Joris.
Very good. Thank you, Orlando. So my name is Joris van Akkeren from the Ghent University, and I was the moderator yesterday of the Young Researcher 3 minutes presentations. Actually, really a challenge for the people, and many or most of them have never done that before. They were well prepared, I think, and they did all a very good job. So when I'm announcing the winner, that does not mean that was the only very nice talk. We had 30 very nice talks. And you can actually, I'm not sure whether they're already online, but they will be online. This is the first time that we do that. And so every talk was recorded and you can follow them online and see them. It is my pleasure that I can announce the winner. This afternoon, number 2 and number 3 will also be informed. But I can say that the winner was actually selected both by the expert team as the winner, as well as by the young researchers themselves selected the first person. So I should now use my hand and say then the winner is... Right. You can read. So you get a 3 minutes talk now, and then you can come forward for accepting your win.
I can with confidence say that in Finland we burn over 2 million tons of lignin each year, probably much more. But if you were the one that were responsible for this lignin, would you want to burn it? Or would you want to do something else? And if any one of us here in this room would want to be more sustainable and move into wood buildings, would we want these buildings to be coated and glued with plastics? Of course you don't want plastics in your walls, and of course you don't want to burn millions of tons of lignin. If we are already now struggling to find renewable options for everyday products, we can't be burning one of the largest resources that we have available. I think that lignin in our societies will be a huge asset if we learn how to use it first. My research focuses on making products with a super high lignin content, as much as I can. And I began by focusing on construction materials, because, for example, concrete is responsible for about almost 10% of the world's carbon dioxide emissions. And one really fruitful approach has been to first make epoxidized lignin. So it's basically grafting epoxy groups onto the lignin backbone and then reacting this with lignin particles. This material becomes very strong, and it can be used, for example, for these beautiful coatings or these strong adhesives. And they have a lignin content of over 90%. And they are just as good as anything you would find in your hardware store, and they're also just as cheap. Because when I developed these products, I worked together with process engineers and sustainability specialists to make sure that they would be just as cheap and more sustainable compared to anything that we have available in the market today. And you also, now the forestry industry needs to listen, you don't have to make any changes to the craft process. So you only have to build a couple of new facilities outside of existing pulp mills, basically turning them into modern lignin biorefineries. Now my vision for this is to broaden the applicability as much as I can. So now it's building materials. Next it could be composites, for example, for glass frames, phone, car doors. Maybe some of you uses these products. And for example, packaging. And if I succeed, our forests will give us a huge amount of an actually useful material that we can use to create a set of sustainable products that will help us make good decisions in our everyday life. Thank you.
It's a preprint, but anyhow, very much congratulations. And you've seen that he really matched content and bringing the story, communication skills. And it's actually what 3-minute talks are about. You try to bring the message, but you also bring content and do that in a way. You use your hands, and I said that was an important one. Probably that was one of your extra pluses on your presentation anyhow. So very much congratulations. This is a preprint, I would say, from your diploma. It's also covering a small price of some money. I think it's 5,000 Swedish crowns. It's not comparable to what the laureates of the prize get here, but at least it's a stimulation that also in the next years we will have very nice presentations in this context. And I have this one as an extra gift that you can share with your colleagues if necessary. So we have some pictures, I think. Very good. Thank you very much. And it's now time for all of you to go to coffee, I think, but I would definitely also invite you to go to all the posters. I mean, the posters are related to the presentations yesterday. I think there's also some printouts over there that you can take with the titles and all that. So you don't have to go all 30 of them, but at least select some of them that might be of interest. And the young researchers that have been invited to be at this symposium will be at their posters, and you can actually address them over there. So thank you very much for indulging with me for this very nice intro in between. Thank you.
Welcome back. There is a lot of energy. We felt it outside, and we will continue here inside. And this morning we cover innovation and research. In the second part of this session, we're going to listen about clothing industry, fashion. Then we're going to move on to strategies, EU strategies and regulation, and then at the end, the perspective of the forest products industry. So we're going to have 3 talks, 20 minutes each, and as I said before, at the end, we will have the opportunity to have questions and answers session. So I'm very pleased to introduce Martin Eckenbach. I learned that Eckenbach means birch bark, which is a very nice biomass that we can consider also for textiles. Martin comes from H&M. You all know H&M. He was also before in IKEA, and now he's heading since 2019 the Circular Innovation Lab in H&M. Welcome, Martin.
Thank you very much. Thank you for having me. Hi everyone, nice to be here. Nice to see so many. My name is Martin Eckenbach. I'm heading the H&M Group Circular Innovation Lab. And today I'm going to speak a little bit about what we do to support startups and innovators to scale up more sustainable materials in a faster way. And also relevant sustainable materials for us to use in the future. H&M Group is a family of brands. H&M is, of course, the largest ones, but we also have COS, Weekday, Monkey, H&M Home, Stories, Arket, Found, and then we have some business ventures as well. I've collected a few of the goals. We have quite a lot of goals in the H&M Group, but I've collected a few of them that I thought was most relevant for this topic. And the first one is that 2025 will use 30% recycled materials in our products. 2021 we reached 17.8%, but we are still struggling with increasing that. And I'm positive that we will reach 30% until 2025. All polyester used in our products will, by 2025, be 100% recycled. All wood used in our products and packaging will be made from FSC-certified materials or fibers from alternative sources such as agricultural residues or post-consumer textiles. And that's also something we're working very hard to increase, the textile-to-textile recycling. We will only source from producers of viscose and MMC fibers that have good environmental practices such as closed-loop processing of water and chemicals. And this is also very important for us. By the end of 2030, we will only use 100% recycled or other more sustainably sourced materials in our supply chain. And to live up to this, we started in 2019 the Circular Innovation Lab to try to speed up the development in the industry and try to help all the innovators and startups out there. Because we saw that the materials that we need in order to reach these results aren't available in large scales, in large volumes, and in the specific demands that we have. So we need to support the innovation community to scale up. And the first thing we did was that we tried to map out how do we work with innovators and startups within the H&M group. So in these pictures, you can see Circular Innovation Lab, which is my team, working with scouting, testing, evaluating new and interesting processes and materials in our supply chain. And we're doing that in close collaboration with our brands, of course, because the brands are the ones that are demanding new sustainable materials. They're demanding a certain quality, a certain hand feel, a certain touch and feel of the materials, so to say. And through the brands, we're also working together with our supply chain. So that's the channel out to our supply chain, because we don't own our production, but we have a very close cooperation with our supply chain. So that's the one we're using to evaluate these processes and materials in real life. And that's very valuable when you are a small company with small volumes at very high prices, to be able to have our supply chain open up to evaluate the materials. We also have the H&M Co-Lab, which is a vital part in this innovation ecosystem. They're doing equity investments in startups. And what we are doing is that some of our projects might be part of the technical due diligence for them to then make an investment. But we're also able to work with the companies within this portfolio to help them to develop their materials, to steer them in the right direction, to have the connection to our brands, and also to have the connection to our supply chain. Because equity money is one thing, and our project funding is a totally different thing to develop. Then another part, which is the H&M Foundation, and H&M Foundation is a total financial separated entity from the H&M Group. So we don't have that kind of connection. So if another brand reaches out to H&M Foundation, they have to give them the same information as they give to us. But they have something that we are using quite a lot, the Global Change Award. This is a competition where you can apply for 1 year incubation with a vast network of industry players and also some funding for your projects to develop. And we are, of course, talking to all the winners and many of the applicants that are applying for this Global Change Award. And while they are also attending to that, we are able to start up projects to develop their materials and their processes. So wherever you are in your process, we are able to keep the contact with the different players in this area. Which means when they're ready, we are able to support them in the best possible way, whether it's equity investments, whether it's project, whether it's a project where we develop or help them to evaluate their products, or if it's time for a small collection to put it on the market, to put it on a real trial. So in our projects, the thing we do is basically to take it from lab scale into bulk scale. That's our aim. And we realize that when you work in Petri dish volume in a lab with professors and PhD students, the cost is quite high for these materials. And we're fine with that. We can handle that kind of cost. But we need to see in the long run that the cost is coming down and reaching relevant price points. And in this case, we're looking at what kind of feedstock are you using? Are you using conventional production equipment? Is the feedstock available at a global level, and so on? Another thing is that almost anything can be produced in a lab, which means that everything is possible. It's a total different ballgame to move that into industrial production. And this is also something we're trying to help these companies to do, to have industrial partners or our supply chain to help them, or find ways to scale up into industrial scale. Because a lot of hurdles will be present on that journey. Another thing we look at is that in the beginning, most of these companies are positioned in larger cities in Europe, North America, or Asia. But for us to have them as a relevant supplier of raw materials and our feedstock, we need to have them at global scale and global availability. Is it possible to set up this production on a global scale? And of course, in the beginning, we can produce small patches of fabric. We work with everything from a couple of grams of fibers up to 200-300 kilos of fibers so that we can make a small collection. But the most important part for us is that we can evaluate something that we call hand feel. And this is very unspecific, unscientific value, which is used on a daily basis within the H&M group. It's when we come with the material. And you can, I would love to say that the degree of polymerization is the best measurement, whether it's a good fiber or not. But we can't say that. We need to create yarn, we need to create the fabric that is matching, and we need to put that on the table to show it to our designers and product developers. They will then pick it up, use their fingers, and evaluate the hand feel, which is very difficult to specify in an early stage. But that's reality, and that's something we need to take into consideration when we start developing these fibers as well. Another thing we realized starting up, we saw the innovation evolution, and basically we have quite a lot of companies down in lab scale, companies, research institute, universities. There are a lot of good ideas out there, and we are and have been historically quite good at monitoring these. We have our brands constantly monitoring the innovations coming out. We have CoLab investing in these companies. We have ourselves, and we have quite good view of what kind of innovations are out there. In the other part of the scale, the bulk scale, we are quite good as well. We have a mature organization to take care of large volume and to procure that. And in this part, I mean, you need all the certificates, you need all the global availability, you need the price points and everything else. What we haven't been that good at is supporting these companies in between lab scale until they reach bulk scale. And this is what we're trying to do now. We try to support them while they have very low volumes of pricey materials, until they are more ready to increase the volumes, still at high prices. But if we can support them during their journey, I think they are able to scale up much faster. And this is also where you build your pilot factory to prove to the industry that this is working. This is a process that we could scale. And also, this is a product that has a demand on the market. And that's also what we can help and support the innovators with, to have that connection to the end customer. And this might take 10 to 15 years to reach from lab scale into industrial scale. And that's a very long time. And our goals are 2030. We have also 2040 goals, but we need to start now. in order for us to achieve our goals. And hopefully we can decrease this amount of time, but it's quite difficult to build up a new industry around a new fiber. So we need all the support we can have, and the innovators need all the support we can give them. Also the demand. What kind of demand do we have as H&M Group? This is our 2021 H&M Group material basket. And as you can see, the main portion of that is cotton. So about 62% that we use is cotton. 20% is polyester. Then we have 5.6% wood and MMCF. And then we have a couple of other materials like leather, wool, nylon, and so on. So what are we doing in these different areas? For cotton, for example, which is the most important material for us, we are working quite a lot with organic cotton. We're also supporting in conversion cotton, which means that farmers that want to remake their production of cotton from conventional cotton into organic cotton. It takes like 4 years about. During that time, we support them by buying from those farms in order for them to do that transition, because they will lose money, they will lose yield in their production and so on. So that's a way to support them into taking the right decisions. We also have Better Cotton Initiative, which is an organization that is monitoring and helping farmers to grow cotton in a more responsible way. We also try to use more recycled content in the cotton. That's what we're doing right now. What we're doing on the innovation side, we're looking into, are we able to produce cotton in a different way? Do we need the plant, or could we produce it in a lab? And of course, the lab is just the first phase. We need to move that into industrial as well. But it is actually possible to produce cotton in a lab, in a petri dish as well. Then we are supporting future farming solutions. We're looking into different ways of farming in India, for example, looking into the hydroponic solutions where you distribute water and nutrients in the exact amount that is needed to grow the plant, instead of watering the whole field. And we're also using tents to reduce the use of pesticides, for example. So that's also a way to look into new solutions where we can use innovations. Of course, one of the biggest problems with cotton is the recycling. Today we have mechanical recycling, which is a good way to recycle cotton, but it's not a good way to keep the quality of the cotton, because the fiber length will decrease by each cycle. That's a real challenge for us, to decrease the degradation of the cotton during this process. And then we have another interesting part, and that's the alternative materials. Because, to be honest, we are not looking for viscose. We're looking for cotton. And if you can't have cotton, we're looking for cotton-like materials that could be derived from other wood-based, for example, feedstocks. But we need to have something that is more cotton-like than viscose, because our customers doesn't demand an increase in this 5.6%. They're looking for more cotton or cotton-like materials. And that's the important part for us as well. When it comes to polyester, we are increasing the recycled content. And of course, we're trying to move away. Today, most recycled polyester is from PET bottles. This is not a favorable solution long term, because we don't want to take something from a perfect system where you have PET bottles going in circles, being recycled in the same way. Making garments out of that where we don't really have the recycling scheme to get it into the system again. So we're trying to increase the use of textile to textile recycling polyester instead of PET bottles. We're also supporting innovations in this kind. Textile to textile recycling, we have quite a lot of different projects, and we're trying to set up the projects according to the full chain. So we're looking into how do we collect, how do we sort these textiles, because they need to be sorted, and hopefully not manually, but automated, so that we're able to get vast volumes of these recycled textiles into our recycling processes. And there are quite a lot of steps on the way before we can hand it over to a recycler, saying that here is a polyester-rich content textile post-consumer waste that you can use, because it needs shredding, you need to remove trims, you need to remove metals and other contaminations, and then you have the yield. I mean, the most used material today is polycotton. It's a blend of polyester and cotton. And how do we separate those two without destroying either one of them? And today we're able to remove the polyester, but then we practically destroy the cotton. So we're trying to find solutions for this and to try the full cycle of our materials as well. Alternatives feedstocks, we're looking into bio-based but also biodegradable feedstocks for polyester alternatives. And of course, I mean, there's a huge problem with microfibers shedding from textiles when washing them. If we could use biodegradable materials, it would be great, of course. We also need to look into what is biodegradable. Is it industrial biodegradability, or will it degrade in seawater? Will it degrade once we have used different dye stuff and chemical treatments on it? How does that affect the biodegradability? So it's not an easy task, I would say. You can say that the fiber is biodegradable. It doesn't mean that the garment is biodegradable. So that's also something we're looking into quite a lot. We have quite a lot of projects going into textile-to-textile viscose. How do we take care of the viscose once we have put it on the market? There are quite a lot of viscose out there. We are creating quite a lot of new man-made cellulosic fibers. How do we take care and recycle those fibers once they are coming back? Because we will never say that something is compostable to our customers, because we don't want to give them the opportunity to throw away the garments. We don't want to see it as waste. We want to see it as a resource that we can put in to the circular system again, so we can use it again and again. We're also looking into other more sustainable processes within the MMCF process, of course. We have other materials such as leather, for example. We have a lot of mycelium-based leathers that we're evaluating. We're looking into fermentation quite a lot. How do we ferment the feedstock to be used for future fiber production? Protein-based fibers, what are we able to do with those? Can we make something like wool, or could we do something else with these protein-based fibers? Also the sorting for recycling. We're looking into different projects on how to automatically sort these fibers or these garments coming into our systems. And also using enzymes to break down different blends of materials. So my last slide is basically our material innovation needs, and we have several. I have put this together for this occasion, since it's quite cellulosic based today. We will always promote that we need more cotton, or alternatives to cotton. So alternative ways to produce cotton. Recycling of cotton without quality loss. Are we able to do something about these fibers to prolong them, or are we even able to increase the quality when recycling them? Methods of separating cotton and polyester, as I've been mentioning as well. Then the arrows are quite wrong here, I think. The arrow from the viscose shirt should be going to the sugar for fermentation part. So what are we able to do with the viscose coming out on the market? Are we able to do MMCF with cotton qualities out of it? are we able to detect these new materials in automated sorting, like near-infrared spectroscopy, for example? Could we use feedstock from forests to create polyester-based fibers or polyester-like fibers? Feedstock for elastic fibers, are we able to remove the elastane from the market by adding something from the forest instead? Cellulosic-based surface treatments, we're always looking after surface treatments that are relevant. Cellulosic-based alternatives to plastic, of course, packaging and all the accessories that we use. We have quite a lot of different product types in our assortment. So I wanted to leave you with this picture, and I'm quite humbled to stand in front of this crowd of knowledge. It's a lot of people with great knowledge in this room, and I hope the solutions are out there. We are ready to support them if you contact us, and if you have a relevant product that we can help you to evaluate or to discuss, or if you need any input on what kind of future needs we see on the market, and so on. And I think we'll have questions afterwards as well. So thank you very much for listening.
Thank you very much, Martin.
Thank you.
I think you have triggered a lot of questions in the audience, and I think we can entertain those. I have a question already, but maybe very naive. Is wood the next cotton? Maybe, maybe not. I don't know, but that will be one question that we can entertain. Now I'm very pleased to introduce the next speaker, Dirk van Tichem. Who comes from Aerotex. He's, since 3 years ago, Director General of a confederation of the apparel and textiles industries in Europe. And he will bring the perspective of strategies in the European Union. So a different angle, very important to consider, is part of the equation that we need to entertain here. So welcome, Dirk.
I have two. Let's try. Yes. Good morning, everybody. Thank you, Orlando, for the nice introduction, and thank you to the foundation for inviting me, Euratex, to be part of this very festive celebration, also last night. And congratulations first to the laureates for their work that they have carried out. And maybe a special congratulations to the young researchers which are in the room, which were displaying their posters, because from a European textile perspective, we need more young researchers working on textiles. So I'm happy to see many young people in this room, and I can only encourage you to continue working to the benefit of the textile industry. What I would like to do in the next 15 minutes or so is indeed to explain to you, to share with you how Europe, how the European Union is developing a new framework for the textile industry. How Brussels is reshaping the way we will do business in the next 10, 20, 30 years. And the short answer is there's a lot of change coming. And I'll try to keep it short and simple, let's say. Before that, just one slide of introduction of the organization that I indeed joined 3 years ago. So we are basically the official representation of the entire textile and apparel industry in Europe towards the European Union. So our job, my job, is to promote, defend, fight sometimes for the interest of the textile industry in Brussels. You can see the numbers there. So it's the EU 27 member states, but it's also Norway, Switzerland, Turkey, UK, who are part of the Euratex family. We have the entire, let's say, the entire value chain represented in our industry. So from the fiber makers, whether these are man-made fibers, synthetic fibers, all of them, down to the final product, whether this is fashion, apparel, whether this is technical textiles, medical textiles, home textiles. So it's all part of the Euratex family. And once again, our job is to work with the policymakers to overall make sure that this European textile industry at large remains competitive, remains strong. We do not, just to be clear, directly at least, we do not directly represent the brands, the retailers, although I should say there is an increasingly close cooperation, very necessary, between the manufacturers and the retailers and the brands, as you were actually showing in your presentation about the initiatives you are taking from H&M. So there is more and more cooperation also with the retailers. So let's focus on this EU textile strategy. So a few months ago, the European Commission has published an official communication, they call it, EU strategy for sustainable and circular textiles. It's quite unique that the Commission, European Commission, is developing and publishing an official plan, because that's what it is, for a specific sector. It doesn't happen every 10 years. It doesn't happen every 20 years. They released this on the 30th of March, and I will take you through the main elements. Why is there a dedicated strategy? Why did the Commission, who has a lot of things to do, a lot of priorities, why did they spend time with the Commission, with the member states involved? Why did they spend time to develop this vision for our industry? There are three reasons. The first one is obviously linked to sustainability. Everybody, well, I think most of you are familiar with the European Green Deal. So this European Commission focusing, pushing very much to reduce the environmental impact of the industry, of society at large. Mr. Frans Timmermans, the Vice President, you may have seen him, the man with the beard in Brussels, is managing this Green Deal. And that translates into a lot of legislative initiatives across different sectors, across different activities. And textiles obviously gets into the picture. You know the saying, textiles is the third, fourth most polluting sector. You can discuss, but we do have an environmental impact as an industry. So when the Commission is rolling out this Green Deal, automatically they fell into the textile sector and saying, guys, what are we going to do to reduce your environmental footprint? So that's the first and very important foundation for this textile strategy. Second, though, this Commission is also trying to strengthen the industrial base in Europe, trying to reduce our dependency on external supplies. You may remember the story of the face masks, also probably here. And so there is a plan, an industrial strategy that has identified 14 what they call strategic sectors of the European economy, where Europe says we need to invest, we need to innovate, we need to support those 14 sectors. And you can see textiles, we can read it, is one of those 14. So in other words, the Commission is saying, guys, you have an environmental problem, but at the same time is saying textiles is important. And we want the textile industry in Europe to remain, to be competitive, to be resilient. A third element underlying this strategy is the Commission or this European Union has changed, let's say, or is evolving its relations with third countries. Changed from traditionally the EU being very free trade focused, without questions asked, I would say, towards a more critical relationship with our third countries' partners. Thinking of China, thinking what happens in Myanmar, things what happens in Brazil with the forests, etc. So the EU is becoming more critical and is therefore adapting its trade policy, its relations with those third countries, to be a bit more, as it's mentioned there, assertive, so a bit more critical. And that, again, has an impact on the textile industry. You know that textiles is officially the second most globalized sector of the European economy, with strong, intense supply chains. So as the Commission has step by step changed its trade policy, so its foreign relations, you may know, but free trade agreements with India that are in the pipeline, GSP, I don't know if there are trade experts here in the room. So that has an impact on also the textile industry. So based on, let's say, those three main tendencies, the Commission published this strategy. And I just want to go through those 5 boxes because they really summarize the essence of what is the vision. So where does Europe want to go in the next few years? So please read with me the first box. So the EU vision is to say that all textile products placed on the EU market, so regardless where they are produced, all placed on the EU market, are durable, repairable, recyclable. To a great extent made of recycled fibers, free of hazardous substances, so chemicals, produced respecting social rights. That's what the Commission wants to see happening. So these type of textile products should become the reference, should become the norm on the EU single market. And it was interesting to hear your presentation, the H&M targets. They fit within that plan. So H&M has a good intelligence, obviously. But it's important. It shows that companies, retailers, large retailers, already anticipate what is the vision of the Commission. So it's a very strong statement, and I will explain in a minute. It's not just words. This will become law, rules, restrictions. So it's not a nice idea somewhere in developed by a bureaucrat in Brussels. It's hard legislation. Second, it's a slogan. It's not, to be very clear, it's not the Eurotext slogan, because sometimes people confuse. It's the slogan of Vice President Frans Timmermans, Vice President of the Commission, when he said, fast fashion is out of fashion. Sounds good, no? As a politician, to say this. Consumers benefit longer from high-quality textiles. The same idea. So to move away from this quick buy something, wear it once, throw it away. So durability becomes the norm. Reuse and repair services becoming widely available. So you wear something, there's something broken, instead of throwing it away, set up an industry that takes back, repairs, reuse, etc. Number 4, which is very important for us, of course, representing the industry, to have a competitive, resilient and innovative textile sector where producers take responsibility for their products along the value chain. That means due diligence, that means we need to know how that jacket has been made. Where does the fabric come from? How was it made? Where does the yarn, where does the fiber come from? And some of you are familiar, there are very political, complex discussions on the origin of fibers, for example. But again, it's important that the Commission recognizes that we need to have this competitive, resilient, innovative textile sector. And then number 5, and it was mentioned, I think you mentioned this morning, moving away from this traditional linear business model towards a circular business model. That's very much the bottom line. So move away from, you produce something with your supply chain, you use it and you throw it away, you burn it, whatever. We move into a circular business model. So circular, rather than throw away clothes, have become the norm, with sufficient capacities for recycling and minimal incineration. So this capacity issue is indeed a big problem. How do we develop and generate sufficient recycled material to produce all the textiles and garments that we need in Europe and worldwide? So this is the kind of the main 5 topics, and I think you've found that clear enough. But what is important is that that vision is being translated into legislation as we speak. And on the slide, it's a summary. It's not even the full list of regulations that are being discussed. And I'll try to keep it short, but so under this regulatory framework, the first and most important is the eco-design regulation. I don't know if you have heard about this. This is a piece of legislation that will basically decide how you produce your textile products in terms of composition, the quality, the standards that you will have to comply with, the durability, that will force you, to adapt your information and communication of your product, the transparency, the traceability. So it basically will force you to produce your products in a different way than you might do today. There is big negotiations going on what is called the product environmental footprint. I don't know if some of you are familiar with the concept of PEF. Very, very difficult discussions. It's trying to set an objective reference. What is the environmental footprint of a t-shirt? And if that t-shirt is made from cotton or from polyester or from some other material, how do you measure that? What we try to do in this PEF is to set a benchmark, to say the reference t-shirt environmental footprint is X. Getting to this X is very, very complicated. The cotton people will push the framework in one direction. The polyester people will push it in another direction. And I can tell you there's big discussions involving some of the brands very much. But the idea, the ambition is to have an objective as possible reference, to avoid confusion about what has the bigger environmental impact than something else. There's a lot of discussion, more than discussion, preparation to introduce an EPR system, an extended producer responsibility. It's a kind of a tax. People don't like to use that word, but it's a levy. When you buy a textile product, a garment, there will be an additional levy on that product that should be used to finance, I would say, the whole recycling and reusability of apparel products. It already exists in France. If you go to France and you buy a t-shirt, you pay 10 euro plus a few cents. And those few cents are collected and put into an organization, which is called Refashion, which is, I would say, managing, coordinating the whole recycling of all the garment textile products in France. There will be compulsory an EPR in every member state, also here in Sweden. And it's a big discussion. How much will that tax be? Who will collect it? And for what will it be used? Is it additional income for the government to fill their deficit? Or can it be used by the industry to indeed finance recyclability, innovation, etc., in the making? There's legislation on due diligence, so more than before, companies are responsible for what happens in your supply chain, starting from the brand to the fiber. The Commission would like to have every single textile product to have a unique identifier, a unique passport, digital product passport it's called. A lot of discussions, how can we do that? Millions of products, but discussion is ongoing. Working on the microplastics, it was mentioned before. Try to reduce chemicals, big fights on certain chemicals. Try to address overproduction. So brands, I'm sure you know it, will be held responsible for products produced but not sold. So they will have to declare which part of H&M, sorry to always use H&M, but you are here, which part of H&M volume has not been sold. They will need to declare, and obviously that will put pressure on H&M to reduce overproduction, to make sure that we don't have this, overproduction. They also want to introduce a new eco-label. I know we have too many labels already, but the Commission dreams to have a more simple tool of information towards the consumer. So like in electronic appliances, A, B, C, D, E, you know that also here in Sweden, they dream to have something similar for textiles. How that would work, nobody knows. But there is compulsory textile waste collection already today. And so by 2025, you can no longer throw away your products. We cannot ship them anymore to Africa. So we need to manage, as Europeans, our own textile waste. And as Eurotex, we've done big studies with the help of a consultancy. We will have between 8 and 9 million tons of textile waste in a few years. How are we going to manage that? How are we going to turn that waste into value? We have a project called the Rehabs, where we're working with the industry to turn that problem into an opportunity. That's a different discussion. So a lot of legislation, actually there is more, that is in the making, and that will be rolled out in the next, let's say, between 2 and 5 years. So it's going to take a while, because it's very complicated, it's very technical, it's very political sometimes, but it is coming. And again, the direction, I think is clear. Quickly, along with all that legislation, there is also what we call a transition pathway. It's a nice Brussels bubble word. It's basically the Commission with the industry is developing a plan, like a work plan, to accompany that whole transition. So to make sure that the industry, the sector as a whole, can make that transition while remain more or less competitive. That's the plan. So there's a lot of work on resilience, so really studying what are the elements of resilience for the European textile industry. How can we support that? There's a lot of discussion on maintaining the level playing field, making sure that if European industry is moving up the bar in terms of quality, durability, etc., probably also costs, how do we make sure that our European companies can remain competitive vis-à-vis global competitors out there? Market surveillance. Again, the idea is that every product placed on the EU, on the single market, will comply with chemical use, etc. We import 25 billion pieces of apparel every year in the EU. 25 billion. How are we going to control 25 billion pieces? Big question mark. We need to work on that. But so, this pathway is all about, again, more the operational side. It's about investment in innovation, what you said before again, the need to invest in new technologies, new fiber applications, skills, so attracting young generation to work for the textile industry, make sure they have the right skills. It's all about, you know, as we call it in Brussels, making this green and digital transition. I'm almost there, so this is just, if you want, the industry perspective. So from Eurotex, on behalf of the industry, how we look at this whole transition. Can it work? Or how to make it work? I mean, that's how to make it work without destroying the European textile industry. I mean, that's the bottom line. And this summarizes a little bit our vision. First of all, this regulatory framework is okay. As an industry, to be very honest, some of my members, entrepreneurs, are a little bit reluctant. They see all these rules coming from Brussels and they say, there are too many rules. The textile industry is moving from an unregulated to a regulated sector. That we need to understand. And some people don't like it for political, philosophical reasons, but this is happening. We are being regulated much more than before. So what we say is that to make sure that the quality of that regulation is critically important. Meaning, if we set the bar high, is it high enough to be ambitious, but is not too high so that companies cannot achieve those standards? If the Commission would say, we want in 5 years, all apparel products to be made from recycled material. It's nonsense, because there's not enough recycled material out there. So that's what I mean. We need to have a very close, and we are having a close dialogue with the regulator to make sure that this framework, this new framework, is realistic, is enforceable. For example, they say we will ban 1,000 chemical products. You can no longer use 1,000 chemical products. But in fact, we don't know how to control it. Then we have a problem. If you put in a regulation that you will not, that upfront you will say we will not be able to control, why do you issue the regulation? SME friendly, coherent, etc. So the quality of that framework will be critically important. Second, we are as an industry pushing and pleading for support. The European textile industry is 90% more SMEs. Everybody knows the larger brands, clearly, but the producers behind, if I may say so, it's not Lenzing. It's many, many small, medium-sized, family-owned companies who do not have the resources to invest in green technology, in digitalization, in reskilling their people. So we are discussing actually with the Commission what we call a textile transition fund. So basically a big program that would help those companies, with financial support, with investment in research and innovation, in people. By the way, in energy, if I may, our biggest problem today, regardless of all this, is energy. Maybe less so in Sweden, but in the rest of Europe, and you probably follow the news in Brussels, it's our biggest problem. Some of our textile companies today are closing down because they can't pay the energy bill anymore. Closing down and relocating to Turkey, into Asia. So this whole reshoring trend that was happening because of the energy crisis is pulled back in a way. It's a side comment. So, second, we need that support. And then thirdly, very, very important, we need to make sure there is a demand for sustainable textile products. If consumers don't want to buy and don't want to often pay a premium for a sustainable product, it stops. We're finished. We can, as an industry, we can be committed to produce more sustainable fabrics, products. The regulator can create a beautiful framework. If there is no market, if there is no demand, what do we do? So here, we need to work a lot with the brands, with the retailers. We need to inform the consumers. We need to be more transparent, more clear, maybe simple in our communication. But there's a big, big effort to make sure that the consumers come on board. And we need to address the price problem, the cost of sustainable products, especially in today's economic situation. I think we all know how consumers suffer from inflation. It's very delicate to tell the consumer you have to buy, a jeans that was made of sustainable fabrics if it costs 10, 20, 30% more. If that same consumer has, challenges to manage his or her budget. So we need to be very, very careful on that. But it's something we need to work on. Also on public procurement, the authorities are a big client for textiles. The army, police force, fireware, hospitals. And yes, we should be green, but when it comes to procurement, very often the one criteria that matters most is the price. So there is a legislation on the table, green public procurement, so that it's not just the price, but it's also, the sustainability of the product that is important. So, good regulation, support to the industry, and make sure there is demand in a global context. Again, what I mentioned before, we have to be very careful as European industry, as European society, not to create a beautiful framework, a beautiful kind of setting, if it means that we become less competitive towards our competitors outside Europe, we are in trouble. And then the risk is that we would destroy our industry. So we have to be very, very careful about that. Voilà. Final slide is, what does all this mean on wood-based textiles? I'll keep it very short. It's been mentioned before. 6% of fibers, according to the the statistics I received. So there is a great potential for sure for man-made cellulosics to increase their share in the use of fibers used. And I just want to leave that slide here. If you look at those words that I just throw together, what I mentioned before, durability, eco-design, recyclability, bio-based, these are the buzzwords that are included in the textile strategy, in that vision. And I think wood-based fibers fit perfectly in that strategy. So my very short, simple conclusion is that I think, even though Eurotex is fiber neutral, I should say, but I think there is a great potential for wood-based fibers as part of this strategy. Well, stop here. Thank you very much.
Thank you very much, Dirk. A lot of insights, a lot of things to think about. Very important component, especially one of the components that you discussed, consumer behavior, consumer perception, very important. Now, without further ado, I would like to introduce the next speaker, Niklas von Weinmann, who comes from Metsä Spring. He's CEO of Metsä Spring. He's also sitting in the board of a company that is an alliance with a Japanese company as well, called Wudio. So welcome, Niklas. You can bring the forest perspective and the techno-economic scalability issues that are equally important. So welcome, Niklas.
Thank you, Orlando, and I apologize for the difficult surnames we have here today. I usually are the one who faces this, but today we have a few more. Also, thank you to the foundation for inviting me and my wife to this really great event. It has been really nice, and also thank you for the opportunity to talk about one important aspect. So we are talking about producing fibers from wood. And my presentation will focus on the fact that what would a big company considering investing in a production plant think about this. So I come from a big company, and I'm going to, in this short presentation, go through some of the things we are looking for when we are considering, does it make sense to invest in this production or not? And I think that is eventually then the most critical thing when we have all the science in place. Very briefly about the background. So I come from a company called Metsä Group. Metsä is Finnish and stands for forest, so forest group, if you may. And the parent company of Metsä Group is a cooperative. So if you look for a Swedish company which is almost the same structure in terms of ownership, it's Södra Skogsägarna. We have about the double of these so-called owner members in our cooperative. But nevertheless, my work is innovation, and Metsä Group has an innovation company since about 4 years, which is called Metsä Spring, and I'm heading that company. We have a quite a unique position to push forward potential innovations, but we do have to focus on such innovations, potential innovations which fit the Metsä Group industrial or business ecosystem. So as we are not using, for instance, any eucalyptus in our ecosystem, we cannot look at any potential innovations linked to eucalyptus. We have 3 ways of operating, pushing forward these potential innovations. One is to invest in small startup companies, helping them onwards. The second is the fact that we can also operate our own development projects. And finally, we also help the existing businesses of Metsä Group in terms of research and development. So this is the portfolio today. We have 5 big projects, and obviously one focusing on wood-based textile fibers, which is the topic of today. But we have also other quite interesting potential innovations in the portfolio. And I will, in my next slide, talk about the demo pilot. What does that really mean? I think that is quite important to understand. And please remember that most people, they might have their own definition of this, but at least I watched Herbert's presentation here in the morning, and he was using it in the same way as I am here trying to explain it. So this graph is, of course, a very simplified part. But yeah, and I've cut out the whole lab phase, which we talked about earlier today. But obviously that is typically needed when you are aiming to develop a new production process from zero. You start in the lab at some point. But our activity in Metsä Spring comes alive when you start to think about a pilot plant and then move forward to a demo plant and hopefully all the way to a first commercial plant. So what's the difference in my head between these? Well, to put it very simple, when I talk about the pilot plant, it's a facility with machinery bigger than lab, but the machinery is like in the industry. So they are the same as we call unit processes, same equipment as used in industry, but much smaller. You are typically not operating the whole pilot plant as a continuous process. When you go to demo, I think that's one of the main differences. So a demo is typically built so that you can operate it for weeks to see what happens in the long run. I like sailing, and one way of trying to explain this using a sailboat. So imagine that you have a sailing boat and you want to go for a trip with the family, including teenagers. So if you go to the pilot plant sailing, it's like an afternoon of sailing or one day of sailing, and then we go back, we dock the boat, and everybody goes to their rooms and no problem. You might not even use the toilet in the boat and so on. So you don't see many of the problems, which you would see if you then go to the demo plant sailing, which could be a month with your family, day and night in this small boat. The toilet might be clogging. I didn't know that. You have to solve it, and so on, and so on. The teenagers fight. There's a lot of, not so much space and so on. So you need to go to this scale to understand what kind of problems you might eventually have. And still, you won't know what happens when you run the production plant for a year, because you are not operating the demo plant continuously for a year. So you are still left with some of the risks when you go to the first commercial plant. But this is a way of mitigating the risk in scaling up. So one of the first part of my title of this presentation was scaling up. So this is scaling up a production process. So I promised some views on how we look at a potential new investment. So this is the basics. If you want to produce something, you want to make sure that you have the raw material, first of all. You need to have availability of the raw material, but the price of the raw materials also very important. And in some cases now, when we put this into the context of this wood-based textile fiber, you need to, the available pulp on the market is not directly fitting your process, so you need to think about tailoring it before you use it in your production process. Then obviously you have to have the actual production process with the roof and walls. And as you want the production process in this kind of business to run almost a full year, you might have 1 week of shutdown when you are making repairs, but otherwise 355 days, day and night, it's operating. So you need to make sure that the process, all bits and pieces are robust. They really can handle some small changes and so on. When you are considering investing, you need 2 more things. You need somebody who can engineer or design the actual production plant. And it's not so easy when you go to a completely new field. There are no competencies in the engineering companies. And then you need the equipment suppliers. Again, as nobody has built a production process like this, there are no equipment suppliers who can say, my equipment works exactly like this in this application. So the So the burden of making sure that the process works is on the company, not on the equipment supplier in the first case. Then obviously you have to have a good product. So you need to have a demand for the product, and you also need to have the appropriate quality so that you get a good price for the product. And Herbert was showing nicely how this ion cell fiber is in relation to existing products. Very good position in that respect. But you also need the means to get to the market. If Metsä Group would now start producing this fiber, we have no people who know how to sell the product on the market. We have no distribution chains to ship the product to different places and so on. So we have to think about that as well. Well, this is still fairly simple. Then you need to think about the permits. You need to have most likely an environmental permit. You need to have think about the chemical side, the chemical safety permits, and so on. You need to look at the patents. You need to understand, do I have freedom to operate in this world of existing patents? You need to have the people, both for the investment phase, that's one kind of competence to build the factories, but then also the ones who are operating the one. Now we think about Finland and Sweden, we don't have this kind of operations in Finland and Sweden, for instance. So who would be the ones who operate? We have to educate these people in good time. And again, a demo plant is quite important here. Then you need a site, obviously. This takes quite a lot of land to build. You need to have the financing. You have to go to the banks. Obviously, you need to have your own equity, but also the banks are involved. You need to convince them. They are looking at similar things as here. Typically, the first question the top boss is asking is profitability. So you have to make sure that this all, when you make the investment, you can pay back the investment. And finally, there might be then other things that you compete with. For instance, in this wood-based textile fibers, there is one very strong NGO pushing for adding recycled material. So you need to have their stamp, which is actually a green shirt if you are in the top category. And many of the customers are looking for this green shirt stamp when you are selling the textile fibers. And then the textile strategy. What is going to happen in 5 years in Europe? You have to understand that as well. I'm sorry, this will be the most technical slide, but because my presentation title also included techno-economics, I do have one slide about the technical aspects of going to a market. So this is my term, direct dissolution, and Herbert also used it in the morning, so we talk about the same concept, production concept here. So as I pointed out, for this process, one of the big questions is the availability, especially of the base component of the ionic liquid. So you can buy it on small scale, but not on large scale. So we have to work to have the base component, whatever the base component eventually is, we have to work to have that availability, and rather from 2 than 1 supplier. We have to work on the recycling rate of this solvent because it's fairly expensive. So you have to be in the 99 or even above rates to be profitable. You need to make sure that this solvent, whatever you choose, is stable. We heard from morning's presentation that in MMO you use quite a lot of stabilizers. So you need to study this part. And this really impacts the frequency of changing the spinneret. So imagine this kind of a box which through you are pushing the dope, and then you have the nice filaments coming out, as in the morning videos. And at some point it will clog, and you need to replace it. And if you have like 500 of those, and you need people to do it, so the frequency of changing, if you do it every 5 hours or every week, it's a huge difference. You need to study that. The product properties, again, Herbert did point out these earlier this morning. Very important from a technical perspective to reach these goals. Whiteness could be, especially in non-woven area, a key criteria. and the mechanical things and fibrillation was mentioned. Then you have to understand, especially based on the demo plant, what's your product output. So you are investing in a certain amount of hardware, equipment. You need to know how much product is coming out per year. And obviously, if you push the machines on a medium level, you might get very good quality product out. But then if you go to full speed, the quality goes down. So you need to really understand what is the maximum you can produce. You need to make sure that every time you produce, the product is the same. And finally, I would say most importantly, you need to make sure that the chemicals and whatever you are using are safe for the workers and for the environment. So this is really important. So then to the actual economics of this part. So to put it very simple, you have to invest first money to build a factory, and we call it CapEx, capital expenditure. So you have to make an investment. And then you have the income from selling the fiber, which is the positive, and then you have the cost of producing, which is the negative, and hopefully the positive is bigger than the negative, so that you can pay back the CapEx from the beginning. So this is really important. At the moment, it is very expensive to build. Not only the energy, but all the materials have gone up. The delivery times are really long and so on. So this is not a good time exactly now to build. So you need to also understand the cycles in construction, where is a good moment to invest. In terms of the income, the positive, if you do a profitability calculation and see how sensitive it is, you will find that the most sensitive factor is the price of the product. So if you get 2.5 or 3, it's a huge difference. So you have to really understand what is the product price. And again, from our perspective, we have to also consider the fact that if I use somebody to sell the product, I have to pay that company as well. So I cannot use the end product price in my calculations. On the cost side, the largest single component is the price of pulp, the main raw material. So you have to work on that. Number two, in terms of cost today, is energy, and it might now be even more significant due to the prices, especially in Central Europe. We see in Finland and Sweden, we have more possibilities to integrate and have own energy production, so that could be a competitive edge. And then finally, the personnel cost is also fairly large. You have to understand that this is a fairly intensive in terms of human workers. So you have to be quite, or there is a big difference if you go to Asia and think about the average salary, and then in Finland and Sweden, the average salary. You still need the same amount of people, roughly, except if you can develop the automation to a new level. And this we already talked about. So going back in time, and yesterday Ilkka was mentioning the year 2008. I got involved in 2009, and also Metsä Group got involved in 2009. We started a series of big joint research programs in Finland, including all, let's say it like that. Co-funded, or the main financer was Tekes, today known as Business Finland. Our own in-house research began a few years later, in 2030 roughly. We can debate that with my colleagues, but this is what I've used in this slide. And we have been pushing forward since 2013. One critical thing was to invite Itochu to the project, our own project, because as I mentioned, in those days we had no understanding of the market. We needed somebody who can say if the product is good, who would pay something for this, to what direction should we develop it, and so on. And we went to this Japanese company who has been in the textile market for over 100 years. Then we went to the first pilot scale. You remember the sailing one day or something like that. So pilot scaling actually done at TITK in those years, 2016 and 17. And that again was partly co-funded by the European Commission and especially the BBI joint undertaking instrument. So there's a lot of support from the Finnish government through Tekes or Business Finland in this work. Here you see the T-shirt made in the pilot trials, really big milestone for us. But then we realized also based on the trials in Germany that we don't have enough understanding of how we can recycle the solvent and so on and so on. So we started to plan a demo plant. Now you remember the middle one in my scheme. And we decided in October 2018 to start building, and for that purpose we made then a joint venture with Itochu, and that joint venture owns the facility. Just to give you some kind of understanding, the investment, which is not a profitable investment in the capex of this demo plant, is roughly 35 million euros. So it's a huge amount of money just to make sure that you learn who is going to fight with whom. This is the picture from when we started digging the ground in late 2018. No snow on the ground that year in Finland. So this is in central Finland. This is when the demo plant here in the front, the white building with the black roof, was almost ready. In the background you can see the unit producing the pulp. So we have a concept where we integrate to the pulp production. And this is a very happy milestone as well. In the midst of the pandemic, when we made the first so-called bale comprising of the product, and you can see all people signing the bale. And yeah, was, as you can see from the picture, in the middle of the pandemic. Now it's hopefully staying a bit calmer. So with these few slides and stories, I wanted to shed some light on how we think from a company perspective on this kind of potential new innovations. Thank you.
Thank you so much, Niklas. Wonderful closing of the talks. Wonderful. Now we go to the questions and answer session, and I would like to invite Ilkka and Herbert to come to the podium. And in the meantime, also, we have the other speakers sitting in the front row, so we can dedicate or direct some of the questions to them. So let's make this an interactive process, and the floor is open to you all. And we can just raise the hands, and there will be microphones going around so that we can take your questions. They will be recorded, and as indicated earlier, we're going to have the recordings available after these sessions. So, questions? Maybe I can, yes, okay, there is one question here.
Thank you very much. Patrice Mangin from Trois-Rivières University. Niklas left me on my hunger. Like from starting 2009 in the demonstration, first bale 11 years. Now the boat sailing for a full year and more, which is the commercial plant. What's your timeline about? Because, you know, we have these innovations, which is marvelous, but it takes 15 years to get to the product. The market is changing and the society is changing. So do you have an answer? All of you, by the way.
The whole process, as Niklas said, and we have went over also yesterday, started somewhere 2008. So that's a long time to hear. But actually, in the beginning, there was, I would call it lag time, when we were trying to understand what we are actually doing. And it was only somewhere in 2017 when we actually found those solvents what are being applied now. And it's actually after that the development has been fairly fast. So in a way it also tells a little bit on the time frame of research, because if you're doing research in the laboratory, you're normally working at maximum maybe a few grams. Then you start piloting it like Aalto did. They require something which is minimum of a few kilograms, and there's upscaling to that, and then upscaling even to bigger scales. And every time you're actually facing new challenges. So it's when you're talking about the big process like this one, something which may be a side product or impurity at 1% scale in the laboratory, you won't even notice it. But actually, if you're talking about tens of tons of chemicals, 1% is actually pretty much. And especially in that scale, it also means that we have been actually developing several things, let's say parallel or in collaboration mode, both the scaling up of the solvents, because you can buy these actually from Sigma-Aldrich as research chemicals, but the price for those is far beyond what you could afford actually using in a real operational plant. So there has been development or upscaling of the chemistry, but there has been also upscaling of the technique how to actually make the fibers. And especially when we are talking about the upscaling of making the fibers, that has been really fast in my opinion. So please, Herbert, continue from this.
Yeah, very good question. Of course, process, in general, I have to state, process-related innovation has a much longer time scale as anything else, like IT-related one. And I think to answer a little bit this question, I think it's good to look back. How was that in previous innovations, which finally ended up in commercialization, like the classical NMMO-based lyocell technology. And I mentioned the first patent was filed in 1939, and the first commercial plant came on stream in 1992. And you had 3-4 powerful companies in the back. That's not what we have at the moment. So we are an academic institution. And of course, we benefit from all the developments which were occurring at that time, because we also use this air gap spinning technology. But I would say this is the one thing. The other thing is, of course, also the background and the money you invest. Of course, when you invest more money, research money, but also other money, especially when you collaborate with big research institutions, especially from a company, then, of course, the development might go much faster, because the conventional operation of the processes are there established, while this is needed to be built up in an academic environment first, what also has been mentioned. So when my colleagues, especially in the academia, our president and our dean asks what are the development phases, yes, we start, and in 2 years we know everything what we should know within the pilot plant. In another 2 years we know everything from a demonstration plant, and in 5 years we have the first commercial plant. Bullshit. It's not going to happen. So unfortunately, and I think it's not really a secret, the first, let's say, money you earn from a lyocell plant was not before, let's say, mid of 2005, 2010. And it's very important also for you, Metze Fiber, you have a strong production of pulp and paper to finance your investment in innovation.
Very good. Niklas, if you can respond quickly.
Yeah. It's just unfortunately so that engineering and building a demo plant takes about 2 years. It could have been a bit shorter, but we came just into the pandemic when we were almost ready. But 2 years, then you need to reserve 2-3 years for the actual demonstration work. And then you start again, engineering and building, and the big plant is 3 years. So this is, you cannot really change this if you want to start a completely new production process.
Thank you. More questions, and I would like to ask to make the questions short and the answers also short, so that we can cover as much ground as possible. There is a question there from one of the researchers participating in the poster sessions.
Yes, thank you. My name is Alexandra Kozłowska. I'm from Chalmers University of Technology. I have a question to Dirk, actually, from Euratex. I mean, it's so nice to see that you, of course, create in the European Union is working so hard on the creating new legalization. And of course, we are all aware of the drawback of the fast fashion. But what about the education of the society and customers? That's something also what Orlando highlighted at the end. I would like to know if the European Union has any plan to advertise what are the drawbacks and what is the advantages and how to change the thinking of the society.
In the textile strategy, the need to focus on the consumer is recognized. The Commission is proposing a campaign which we'll call Refashion EU, like #Refashion EU. We just announced that they will roll out the campaign. We don't know any details. So you can say at this stage, the Commission recognizes that we need to address the consumer. We as an industry insist on that. As I said before, we as an industry increasingly work with the brands to kind of join forces into educate is a strong word, but inform the consumer about environmental impact and etc. So I would say the good intentions are there, but there is work to be done in the years to come. So to make sure that it's not just good intentions, but that we actually roll out this campaign with resources, with transparency. I mean, we have too many labels. We have too many green labels. Every brand is using its own green cards, whatever it's. So we have things to do on our side in being more transparent, and then we need again joint forces between the authorities, the industry, and the brands. So let's hope it will. At least we will try to push to make sure that it actually happens. It's not just intentions.
Thank you, Dirk. I think we're all consumers. I'm a consumer, and I have a question, actually. So I tell my students my favorite suit and pants are the ones that I used in my PhD graduation in '98. And I still use those. I should have brought those today, because really I use them as an example. They are pretty much a lot of polyester. So my question to the speakers is how far are we from getting this long durability, in the polyester-like materials? I mean, what is the development that we need to see in this direction?
Yeah, good question. So I tried to, in my talk, I tried to emphasize the criteria relevant to durability of textile fibers. So one is certainly the integrity of the fibers. That means also the intrinsic strength properties. So that's an issue, but not, of course, only under dry conditions, under wet conditions. That's very important. And I think H&M quoted that they refrain from using viscose fibers, probably because they have some, let's say, not very good properties under all circumstances. That's understood, of course. But I would say the new generation of lyocell type fibers, they are very cotton-like. So we have certain challenges. This is the so-called fibrillation. The fibrillation is a property which is more or less an intrinsic property because of the high orientation of the molecules. The lateral adhesion between the crystallites is weakened, which then facilitates the split off of surface fibrils on wet abrasion. That's a point. But there are ways to remove, to inhibit that, or to at least reduce this degree of fibrillation. I would say we are in a good way to be able to produce durable fibers. Of course, we are talking about cellulosic fibers or natural fibers. There are certain properties which cannot be attained using cellulose or natural fibers. Cellulose is a very hydrophilic polymer, as you know, and it's terribly difficult to render cellulose, let's say, a permanent hydrophobicity. That's the problem. So for outdoor applications, we have also with our students, we try a lot of options, but let's say to combine both green chemistry methods, don't use any fluorhydrocarbons and silane-based compounds and so forth. And in addition, also to ensure biodegradability is very difficult.
Thank you. Very quickly, Ilkka.
You were asking for short answers, but if the questions are like this, I mean, there are no short answers. The thing is that in every fiber or material made by man, like polyester, there are different qualities. Your suit is probably high quality because it's rather old already. On the other hand, it was actually pretty clear from what Herbert said today. It's the similar situation in man-made fibers. So there are applications where you don't need such a high quality. And then you can use different raw materials. And then on the other hand, you have the other end. So it also balancing, and there is actually a lot of more parameters behind this. So maybe that's...
Definitely. One question here, and if there are more questions, please raise your hand so we can locate you and have the microphone on time. So please, any other questions, raise your hand. Please.
Is there a difference between different wood fibers for textile?
Indeed, yes, there is. So we basically summarize this category of fibers in so-called either man-made cellulose fibers, that's one title. The other would be regenerated cellulose fibers. But that does not include, for example, cotton. So that's a natural fiber. And these regenerated cellulose fibers, the typical grades are depending on the processes you use. The viscose process, for example, is of course determining to some extent the resulting properties. Even though, and that's quite nice, we have an expert here on viscose sitting in the audience who could explain it much better. But the viscose, why is it still alive? Because it had the highest flexibility in tuning the properties compared to any other process. So it was already thought that it will die after Second World War. And then a person named Cox invented a modifier. Adding this modifier was capable of extending the state where you can stretch this solution so that the molecules align in parallel, which give high orientation, and that way then these so-called high wet modulus fibers, which are very, let's say, comparable to cotton fibers, modal fibers, for example. So, and then of course the other type is the lyocell type fibers, which use a direct solvent, using also a different type of spinning technique, which results, let's say, intrinsically to higher tenacities and higher properties, especially under wet conditions.
Ilkka, you want to complement the answer?
Yeah, I'll be very brief. We have to remember that there is actually, it was actually shown in Herbert's slides that there are other emerging technologies like the carbamate process, which is being scaled up with this Finnish company Infinity Fibers. There is mechanical treatments like what Spinova is doing. There's cold alkali or alkali, different types of solutions scaled up with other companies. And I don't think there is actually competition, because how I see it is that it's just a palette of opportunities. And of course, in the end of the day, we have to see the whole palette to make correct decisions. Is this process viable for the textile fibers, or maybe the other one is for non-wovens, and the third one for something else?
Yeah. There is a question in the back.
Yes.
Gabriel? Yep.
Hi. Gabriel Bonville from the University of British Columbia. I have a broad question, so it's for the laureates and maybe also Mr. Eckenbach from H&M. So in the ion cell process, you chose to produce fibers in order to have a fabric as a final material, right? But in theory, you're not limited to producing fibers, and you could shape the cellulose solution into any shape, for example, film extrusion, right? And you could even change the surface to change the filling. So do you think your technology could change the way we produce clothing by directly processing it into the desired shape without having to use fibers as a transition material? Thank you.
Thank you for the question. Actually, it's even more than just putting it into different shapes. Yes, that should be possible. It's not yet there, but there is also another rather unique property of these solvents, because you can also use them for chemical modification. So it means that you can have different types of materials from cellulose. I mean, nowadays the other modified cellulose products is basically more or less like cellulose acetate. But here we can actually make a lot more chemistry. For example, there are already good examples of producing cationic cellulose, which is a water purification chemical. The beauty of that is that you apply it for precipitating the particles from wastewater. But after it has done the job, it actually decomposes back to cellulose, and that is biodegradable. So actually I see this, that you might have one line which is actually using the same dissolution technology used for making man-made fibers, but then you can have side pipes also to produce other products. So it's not only that we are talking about textiles. Yes, there are other possibilities, definitely.
Martin, do you want to add anything?
Yeah, I can add, I mean, we're looking into several opportunities with cellulose as well. It's looking at sequence, for example. How do you create these small shimmering effects on party dresses or kids wear from cellulose? Or how do you create accessories from cellulose feedstock as well? So we're looking into all what you can do with cellulose-based feedstocks as well. I think to create something else than fabric, to create textiles, then you are quite limited to creating like panels for garments, and that's quite a small area. But for other applications, definitely.
Thank you. Maybe you could mention that. Other questions? I was noting that in the investments that I see startups, actually a lot of funding is coming to biology. And that was one of the H&M's ideas, to grow cotton in the lab. So do you see synthetic biology and biological methods to build molecules up as a possibility in this area? Given that what I see is a huge investment, actually the largest in startups are going to biology routes.
Yeah, very difficult question because I'm not a biologist, but I have a clear idea on that. This is also due to the age, advanced age. There was a professor called Professor Brown, and he wanted to raise algae in the Bay of, was it Florida, to produce algae, but of course never worked out. And also to use carbon as a source for fermenting new biopolymers is not a good solution. We have the best biopolymer with the cellulose and other biopolymers. So I'm not at all convinced. I know even big companies like DuPont try to use, let's say, biochemically produced biopolymers like Kurtlan or 1,3-D-glucan and make very bad fibers out of it.
Okay, different opinion, Ilkka?
Not a different opinion, but actually, if you are using fermentation, like we are producing beer, I mean, then we have the yeast, which is basically also containing proteins. And actually, these particular solvents, what they are talking about, they are pretty good solvents for proteins. So, yes and no. So maybe not for the cellulose, but actually there might be possibilities in the side streams, which is not at all looked at least to my knowledge.
Yeah, good point. More questions? There is one there.
Yeah, thank you, Maija Tenkanen from University of Helsinki. Actually, following up this question, a little bit like intriguing thing is that, do we need trees? Can we have it as a cell culture? It was discussed about cotton, but what about, I mean, if cellulose is so great, so do we need to have the forest for that? Or can we make it more? I know that you are not an expert on that, but kind of a Orlando's question like activated me to ask this.
Yes, we do. The thing is that yes, there are possibilities in making these kind of things, but actually, if you use actually cells to produce something, for example, thinking about Finland, I mean, we have a winter, so it doesn't. It's not. I would claim that it's not yet there. We have much better biochemists and biologists here in the audience. I'm sure Kalle Kahnberg could, for example, answer that question much more detailed than I am capable.
Yeah. I didn't want to distract from ion cell to biology, but I think it's a relevant question to ask. So very good point. But maybe Johanna.
Yeah, just to comment, so that when we are utilizing microbes to produce something, we need carbon and nitrogen. And where does the carbon come from? Do we first grow the tree or the plant, then we degrade it to monomers, then it contains inhibitors, which are attacking the microbe, they are not letting it to work as it should. And then we are doing very tedious downstream processing on the liquor. I have been working with this fermentation of biomass hydrolysate, so I know it's not that easy. So maybe we could utilize the wood or the plant.
Herbert.
I fully agree to that. But there is another point I would consider. We have Mother Nature makes so excellent biopolymers. And of course, we talked about wood now, but we have also annual plants, we have agricultural waste, and I think that is certainly the second most important source for the future. There is one, looking to H&M, there is one intrinsic disadvantage, or actually more intrinsic disadvantage of cellulose. It does not melt, so we have to basically make a sidestep to produce a kind of spinning solution by selecting a good cellulose solvent to eventually increase the cellulose concentration. So there is already a progress. When we look at viscose, we have, let's say, in the best case, 9% cellulose in the solution. Now we talk about 13 to 17%, but it's actually not very good. So we need to go to 40, 50%. Yeah? And the other thing is, you were talking about we urgently need something which replaces elastane. I fully agree. But what is it? So elastane is such a terrific polymer which, to my knowledge, has not ever been, let's say, challenged by other biopolymers. Yeah, not at all. So this is something what we are really working on also. And of course, the other and the last thing is tuning hydrophobicity, hydrophilicity, as I mentioned already, while maintaining the whole material environmentally friendly.
Ilkka.
Not directly related to cellulose, but as a continuation what Johanna said is that actually when we go to a shop now, we can buy a milk can where there is clearly a plastic screw cap, and what they state in this cartilage is that it's 100% bio-based. Yes, it is, but it is polyethylene. So what is being done is that they actually ferment first the sugars to ethanol, then they produce ethene, and then they polymerize it. But it's still the same polyethylene. I mean, this is greenwashing, in my opinion. And in the old days, people were actually using the wastewaters of sulfite paper pulping to make ethanol for other purposes, not to make ethane. And actually, ethane was used to produce ethanol for the same reasons. So, I mean, it's not only that we are talking about this utilization of cellulose or making cellulosic products. This is all over. I mean, in all materials, and especially difficult materials are when these components, like synthetic polymers, are mixed with natural fibers, like the coating of the milk can or something like that. There you have a problem with polyethylene, and I think that's much more severe than we guessed it is.
Major problem. We're a little bit over time. Maybe we can entertain a couple of more questions. Please, Alexandra.
Yes, I have another one actually.
Just the microphone, just a second.
Thank you. It's a little bit more technical from your presentation. I'm quite interested. Why did you see the upscaling of the strength in the cotton post waste? You know, those green and yellow slides you showed. So you said that the strength of the material increased. Is it due to the application of different solution, or is it because of the spinning process? Do you know what?
The answer was given by Frank Meister. The cotton has a very uniform molar mass distribution, and that's essential because when you have a certain share of short chains, as you typically have from wood pulp, this weakens, of course, the fiber. So there is a clear, almost straight line correlation between a certain fraction of short chain and the final tenacity. So we like cotton waste.
Yeah. One more question. Okay, maybe we can close with a question I wanted to ask Herbert again. And this idea of transition between university and industry is a quite important one. And pretty much oftentimes we scientists don't look into what is the need in industry, in society, and there is a disconnect. So how do you see the work?
And vice versa.
And vice versa. So what is the way to bridge that dilemma?
Yeah, I think this is an excellent question. And I like to interact with all the parties, even with institutions like EU. It's important to understand what is going on. And my special concern is, because I see it, young researchers very hungry for research and have of course, their focus typically continuing their PhD work. But this would be the moment where they go out and have a sabbatical in industry and learn the real requirements, what Niklas also mentioned. So this is totally different when you do something in the laboratory and then you want to gradually do it in commercial scale. Yeah. And the same also applies to R&D people from companies or even production people to spend a certain time in academia and to more or less mutually influence each other.
Very important. Okay, I think this is all for today. It was really a big pleasure to host this event. I would like to acknowledge the participation of our steering group, the selection committee, who has driven the process, have made the selection of the speakers, and of course also the laureates. We're very proud of you, your work, and congratulations on our behalf, and congratulations all of you for staying today, asking good questions, and thinking all together about the future of textiles wearing wood. Thank you.